We will now move on to our next keynote address, which is Building Robust Biometric Systems from Design to Deployment by Professor Arun Ross from Michigan State University. He is the Martin J. Vanderploeg Endowed Professor at Michigan State University in the College of Engineering, Department of Computer Science and Engineering. He serves as Site Director of the NSF Center for Identification Technology Research, CITER. He's the Director of the iProbe Lab and Advisor to IAPR TC4 on biometrics. An IEEE Fellow and globally recognized leader in biometrics, his pioneering work in multi-modal biometric fusion, presentation attack detection, and responsible AI has significantly shaped the scientific foundations and real-world deployment of secure digital identity systems worldwide. Professor Arun Ross.
Well, good morning, everyone. It's a pleasure to be here, and I'm thankful to MOSIP and the Kingdom of Morocco for the hospitality extended. And today I'll be speaking briefly about biometrics, and I hope the conversation will spill over into those other meetings as well, and in our personal conversations with each other. So as I was introduced as a professor at Michigan State University, I also serve as the site director of the NSF Center for Identification Technology Research, which has built a consortium consisting of industries, universities, and government agencies. And through that, we are able to perform projects that are relevant to the industry as well as to government agencies. And so researchers are working together with these stakeholders in the field. And if you have any questions about CITER, I'll be very glad to give more information in our personal conversations. So let me begin with a very simple question, a question perhaps which each of you has a great answer for. But just so that we are all on the same page, what is biometrics? Well, it is the automated recognition of individuals, and it's based on their biological and behavioral traits. So we're talking about fingerprints, for example, as a biological trait, and gait or keystroke dynamics as examples of behavioral traits. When we talk about these traits, they ought to have at least two important criteria. They have to be distinguishing, and they have to be repeatable. You want traits that are unique to an individual. At the same time, you want that trait to be reasonably permanent as far as that individual is concerned. So this uniqueness and permanence are two important criteria that define the validity of a biometric trait. And certainly there are many examples, and biometrics has come a long way. On the right-hand side of this view graph, you see what is called as a Burtian card from the late 19th century or perhaps the early 20th century, and biometrics has come a long way since the Burtian card. A number of biometric traits have been investigated, some more than others, and some have been deployed and tested in large-scale applications. Some have only been tested in laboratory environments, but there are a number of traits that researchers and others have explored. And some of these traits are indicated in this slide. You have fingerprints, you have palm prints, you have iris, voice print, signature, face, DNA, the conjunctival vasculature, ear biometrics, keystroke dynamics, dental biometrics, gait, hand geometry, vein pattern, ECG, and the list goes on. And certainly not all have been explored to the same extent, and certainly not all have been deployed in large-scale applications, but it's worth noting that many different biometric traits are out there. So what is the basic problem in biometrics? The heart of biometrics is biometric matching, or what we would call as biometric comparison. This is the heart of the biometric system. You're given two biometric samples. Think of two fingerprints, for example, And now the problem is to compute a score, which is a measure of the probability that these two samples are from the same biometric source, or whether they are from two different biometric sources. Now, the reason why I'm dwelling a bit on that bullet point is because there is a phrase that I used. Well, I said it's a score that is produced, but I also used the word probability. And this might be disconcerting at the beginning, but in reality, this is a problem that is well handled by biometric researchers as well as integrators and vendors and stakeholders. Because what a biometric system produces is actually a match score that is not always perfect. It is not always 100% when it is a match and 0% when it is a non-match. It is somewhere in between. And that is why we use the word probability. And because we use the word probability, we are obliged to define two types of errors. One is called as false match, which is when my fingerprint inadvertently matches with someone else's fingerprint, or a false non-match, when my own fingerprint does not match with itself, perhaps due to some quality issues. But at the heart of the biometric system is this: producing a score by comparing two biometric samples, be it two fingerprints or even two iris images, and so on. So what are the components of a biometric system? And again, the reason for enumerating this is to understand the dynamics involved in constructing a biometric system, really looking under the hood, if you will. So we have a sensor, like a camera, which acquires the biometric data. And then there is a feature extractor, which extracts salient and discriminative features from the data, features that can be used to distinguish individuals. And then we have a comparator or a matcher, which compares two extracted feature set and produces a score, which I alluded to in the previous slide. And then you also have a database or a gallery, and this is to store the biometric data or the reference data or just the biometric templates, which are then used for the recognition exercise. So we see that many different components are involved. When we talk about sensors, we really need folks who have a good background in physics and electrical engineering, for example. And when we talk about feature extractor and comparator, we need people who are experts in fields like machine learning, AI, computer vision, and signal processing, and so on. But then there is also the database design, because we have a gallery of data and how to store, how to encrypt. So we need cryptographers. So really, it engages a vast number of experts in order to build and design and deploy a biometric system. It must be pointed out that although we use the word biometric recognition as an overarching term, there are really two modes of operation. One which we call as biometric verification, where you have two biometric samples and you ask the question, is this the same person? Do these two biometric samples come from the same source? That is the verification problem, which is a one-to-one comparison. And then in contrast, we have the biometric identification problem, where we pose the question, who is this person? It's a one-to-N comparison, where you take, for example, a face image, and you compare it with a number of face images in a database running into millions, or in some cases billions, in order to determine whether there is a match or whether there is a duplicate, and so on. So very often the identification mode is used for what we would call as deduplication. And clearly the complexities of both these different modes of operation are different. At the same time, there are some commonalities. But clearly, the complexity of face verification, which is on the left of this view graph, is different from the complexity of face identification, where an extensive search operation might be needed. A number of different applications, and one nice thing about being here at the MOSIP event is that we hear about a large number of applications and the innovation involved in deploying these applications. and the number of individuals who have been positively impacted. So certainly I don't have to enumerate. I think just talking to the person next to you will reveal to you the number of different applications that exist for biometrics and the number of individuals who have been favorably impacted by the use of biometrics. So this slide is important because this paper in the academic community really changed the field of face recognition about 12 years ago. In an earlier slide, I spoke about how we have to design methods to extract features from the raw biometric data. But now you have this automated feature engineering process by using large-scale neural networks. And here it is referred to as CNN, which stands for Convolutional Neural Network. And over the past several years, this has changed the paradigm, certainly not just in biometrics, but in many different domains. And the paper that I'm showing here is a paper titled Deep Face in a reputed conference called CVPR 2014. And here the neural network learns something like a function, a mathematical function, which takes the input image and maps it to some kind of an output category. And in the process, as it learns this function, it automatically learns what features to extract from the image, provided you give massive amounts of data, which we call as training data, for this machine learning system or this AI system to learn what type of features to extract. Now, this changed the game because, as the title of this paper suggests, it closes the gap to human-level performance in face verification. And the impact was immediate. For example, the NIST report, the National Institute of Standards and Technology in the United States, when the report was released in 2018, 4 years after this paper was produced, this is the observation they made. They considered a gallery size of 1.6 million identities, not massive, but still large enough. And they point out that the most accurate algorithm in 2018 gave an error rate of 0.002, that's about 0.2%. Whereas in 2014, the best performing algorithm gave an error rate of 4.1%, 0.041. And this is a 20-fold reduction in error, 20-fold reduction over a short period of time. Because in the previous years, those numbers were inching down, the error rates, but at a much slower pace. But once deep learning, the deep neural networks came into play, it almost immediately resulted in a 20-fold reduction. And the authors of the report, they did make that observation, saying the massive accuracy gains are consistent with an industrial revolution associated with the incorporation of convolutional neural network-based techniques into the prototypes. So it is important to note that a lot of things have changed over the past decade. Even the problem of biometrics is being viewed differently as far as extracting features are concerned, as far as designing sensors are concerned. In short, the technology has improved by leaps and bounds, far beyond what was anticipated even back in 2010. And so these deep neural networks have changed the game, but there are some pros and cons, like any other new technology. It's a heavily data-driven approach, which means we require copious amounts of training data. And certainly there are many vendors here, many stakeholders here who have access to data. But how do we access the data in an ethical manner with appropriate user consent in order to build these massive neural networks and to use them for the problem of biometrics? Now, this training process, training this neural network, is computationally expensive. You must have read about the large number of graphics processing units or GPUs that are needed in order to construct these neural networks. But the actual decision policy is rendered very quickly. So training might even take weeks, but the decision can be rendered in microseconds when the system is deployed. And so we see the pros and cons of deep neural networks, but it's important to point out that they've really changed the game in biometrics and also in other domains. So what are the factors to consider for building robust biometric systems? I'll go over the next few slides very quickly just to touch upon them briefly in the limited time that we have, but I hope we can continue the conversation later on. Firstly, intra-user variations. The same person, in the case of face, the same person might look very different in different situations and circumstances. Biometric aging, how do you account for all these things? And these are things which biometric researchers and stakeholders have been actively working on for the past several decades. How do you account for variations in the same user? And not just for fingerprint, not just for face, this can also be applied to the case of fingerprints and so on. Secondly, what about inter-user similarities? Two individuals looking alike, doppelgangers, or twins, siblings, parent and child, and so on. And this can certainly impact the false match rate. But as I said earlier, biometric researchers have developed techniques in order to even distinguish between identical twins. And in some cases, one might have to use more than just one biometric modality to make that distinction. But nevertheless, for each biometric modality, people are developing techniques to not only manage the intra-user variation in the previous slide, but also the inter-user similarity in the current slide. And then noisy data that our previous speakers alluded to. During enrollment, you might have a good quality fingerprint. During verification, you might have a poor quality fingerprint. This could be due to smearing, it could be due to cuts and bruises, it could be due to some residual deposits on the platen of the fingerprint sensor, many reasons, and not just for fingerprints. This can also be the case for face or iris when the lighting might not be very favorable or when there is some kind of occlusion leading to low quality data. Atmospheric turbulence, for example, if you're doing recognition at a distance. And then there is the problem of non-universality, which often is resolved by using multi-biometric fusion, by using multiple modalities. Some people may consistently offer poor quality fingerprint images, and here are examples of a user's print, 4 impressions at 2 different time instances, and they exhibit incomplete ridge information. And this might lead to a problem called as failure to enroll. And so we don't want to exclude individuals. So this is where the use of multi-biometrics becomes very significant, not just in terms of improving and reducing failure to enroll, but also in improving the accuracy of the biometric system. Biometric aging is a real problem. Face images acquired over a period of time of the same individual. And now how do you account for this? How do you change the template periodically so that you can account for the aging phenomena? And not just confined to faces where it is much more obvious, but also in other biometric modalities because biological tissues, they age. And now how do you account for that? And these are issues that biometric researchers and others have been examining, exploring, and even mitigating over the past several decades. And then more concerted attacks. Much has been talked about with respect to presentation attacks, spoofing, altering one's trait or creating a physical artifact in order to spoof someone else. Now, how do you detect these artifacts? And sometimes these artifacts have to be detected not in the physical world, but in the digital world, because you have things like deep fakes and such. And these are problems for which there are solutions. And yesterday we had a panel talking about the many solutions that have been developed for detecting fake fingerprints, fake faces, and fake irises, and so on and so forth. Our deep fakes are becoming an important issue to deal with, especially in the digital world. All three images that you see here were generated by what is called as a generative adversarial neural network, or GAN. In fact, if you log on to thispersondoesnotexist.com, you will see that there are ways to generate these deep fakes. And how do we distinguish these digitally generated images from actual face images obtained using digital cameras? And again, there are many techniques that have been developed and are being developed to handle the problem of deep fakes. You might have heard of morph attacks, where you combine two face images of two different identities and you create a single face image that now matches with two different identities. Which means, for example, a single ID card can be carried by two different individuals because the photograph matches with both identities. And these are problems for which solutions have been developed. Not only morph detection algorithms, but also what we call as demorphing algorithms, where when the system encounters a morph image, it can actually produce two different images pertaining to the two distinct identities that were morphed in the first place. And the reason for bringing this to our attention, and certainly many of us know about these attacks, is to indicate that biometric researchers are already contending with these problems and are trying to mitigate it before it becomes a large-scale problem. And that is why when we design a biometric system, we're not just trying to improve accuracy. We're also trying to improve robustness, trying to improve privacy, trying to improve security, and trying to improve robustness to these types of attacks. Just a couple more slides and I'm through. I want to talk about some new developments. There are so many new developments, and it cannot be confined to a few slides, but I just want to talk about two or three of these developments. One is infant fingerprints. Many of the classical fingerprint sensors cannot obtain good quality prints of infants. And this is often needed for vaccination tracking and so on and so forth. And there are some vendors here who have developed excellent sensors for imaging infant fingerprints. But here is one example from our university, which we constructed about 6 years ago. Professor Anil Jain, my colleague, was involved in it. And this is to generate fingerprint images of infants using high-resolution fingerprint readers. And so again, there is much innovation going on in the sensing part, not just in the algorithmic part. One of the more recent developments is the use of large language models, LLMs. Sometimes we call them as foundation models, just large-scale neural networks. But what is exciting is that besides producing a match score, this can also produce an explanation as to why two face images match or two face images do not match. They give a verbal commentary. And so this also has changed the paradigm. Previously, we had to go with the evidence of just the score, a high score indicating a match, a low score indicating a non-match. But now with the use of large language models, you can have what we call as explainable biometric recognition, so that both the user and the operator see some reasoning as to why a certain score was produced. And that is true not just for face. We have done that for iris, where we can also produce, in some cases, a match score, besides just a commentary as to why there is a match between two iris images, or why two iris images correspond to two different individuals. And finally, generating synthetic biometric data, Gen AI. This has also changed the game. We can produce a large number of synthetic biometric data, in some cases for training these neural networks, and in some cases for enhancing privacy because now you're using synthetic data in order to build your system. Certainly, there are pros and cons to it, and that's a huge discussion to have. But here we see some of the benefits of synthetic biometric data. All the images in this slide were generated by a GAN that we had developed, and so these are not real iris images. These are synthetic iris images. And this kind of data can also be used for rare scenario testing, where we may not have actual real data, but we can use synthetic data in order to test the performance of algorithms in rare scenarios. So let me conclude with this summary. From an academic standpoint, biometrics is a fascinating pattern recognition problem. I've had the pleasure of working on this for the past 25 years or so, and every single time a new problem sprouts up, it is a great opportunity to see how that problem can be resolved. It's a fascinating pattern recognition problem, but it doesn't stop there. We have seen the benefits in society. And so this is not merely residing in the portals of universities, but it's being deployed in smartphones and in applications that touch the fabric of so many people's life. And then there are advancements in AI that have opened new opportunities for biometrics. Gen AI can lead to the generation of synthetic data. Again, there are pros and cons. I talked about some of the benefits of using synthetic data. There are methods to detect various types of attacks, and some of these methods are generalizable. That means they can even detect attacks on which they have not been trained on. And finally, biometric researchers are not oblivious to the problems of privacy and ethics. It is very important that as we develop and design these biometric systems, that privacy and ethics are not afterthoughts, but that they are done by design so that we can not only improve the accuracy of these systems, but we continue to accord privacy to the end user. Thank you very much, and I appreciate the opportunity to present.